start with the reminders before. So, hi. Let's start with the reminders before everybody joins us. Just, Burcin, I don't have your talk. Your talk. Yes, please. Yeah. Okay, so Burcin will upload her talk. You can upload it to the page and then we download it here to the LCW page. Great. But otherwise, we are ready. So let me remind you the code of conduct. Harassment and professional conduct is not permitted. And here is the contact of people that you should contact if you have, if you witness something. For the COVID-19, if you have questions, please contact the Rubin 2025 COVID, and please look at social batteries in people if they don't want to have social contact. Virtual participants should be muted when you are not speaking. And please, if you ask a question, wait that the Uni-Christian will call you before asking it. The in-person participants should speak only in the room microphone. Brian has the microphone. You just ask to speak and he will come to you and give you the microphone. And so that the virtual participants can hear what is said. There is a Euclid, a Rubin Slack space, and please look on the LCW25 Slack space to find this session. Okay, so our first talk is Agnieszka Polo, and we share. There we go. There we go. Please, Agnieszka.
Okay, thank you. Thank you very much. So my talk will be a composition of a few glimpses from the research we are doing, not going very deep into details, but I hope that maybe it stimulates some discussion later on. So firstly, all the, okay, maybe I can make full screen or better not, if I know how. Yesterday I knew how, and right now okay. Okay. So here is a not complete group of people who contributed to this talk, but at the National Center for Nuclear Research in Poland, we have a very nice astrophysics department, and in this astrophysics, we have a very nice group which is doing extragalactic astrophysics, and in particular, we have high hopes for the LSST data. So the title of my talk accidentally was very close to the title of the talk Uni-Krishnan presented you yesterday, and it will turn around more or less the same data, but no worries, we are not going to overlap so much. And then saying something more or less obvious, but maybe useful, why we are interested in low surface brightness galaxies at all. So I was working most of my life on large-scale structure evolution and galaxies in the large-scale structure. And low surface brightness galaxies are, in a way, the last, or maybe not last, but unknown piece in our census of galaxies in the large-scale structure. So maybe when we map them all, we will see large-scale structure a bit differently than we see it now. Maybe we will be able to fill in the gap in the luminosity function, address missing satellites problem, and all that, because they are small maybe we can understand better the feedbacks.
Okay, we
Okay,
need the
I can-
technical support. Brian, can you find out if they can come? I'm really sorry. I don't know what happened. I was just trying to get the other things away and
It broke.
it just
try to
broke. I don't
speak
understand.
without background, but
Yeah, it's better if you have it. Let me try to
Yeah.
share the entire thing for the moment. Yeah, let me try to do like that while waiting for technical support. And I'm really sorry. We're having problems since yesterday. So
okay, maybe we can
which one is yours?
stop share.
No, no, no.
Oh,
Let's
no.
share the entire thing so that
Okay.
you can show yours.
My
Is
sure. It's too small. To
this is
see.
Wednesday, Tuesday,
Thursday.
and it should be here. Dwarfs polo. There we go. Yes, now it should be fine. And I would like to
Minimize that.
this one. Yeah.
Thank you so much, Simona. Okay, so coming back, we hope to understand better the faint end of the luminosity and mass function of galaxies, to understand the environmental role of in the galaxy formation and evolution, different types of feedbacks, maybe even get some insight into properties of dark matter. So, okay, so now for a change, I cannot change slides. Sorry. Sorry. Nothing. Nothing
Change
ideal.
sky. There you go.
What to do?
I clicked on it and then
Okay. 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 Yes, for now. For now. Let's. Maybe we should. Yes.
Christian, are you seeing the slide changing?
Yes, it's fine.
Yes,
Do
so-
you hear Agnieszka?
Yeah.
Okay, so sorry for that. Okay, so on the top of that, these galaxies can appear in many varieties, and these varieties may tell us different pieces of the story about what they do in the context of the large-scale structure. And here we have a piece of large-scale structure from the Viper survey we once participated in, and which will overlap with the future LSST data. So we have bright future ahead. So here about these many varieties, for example, I mentioned in the last point that low surface brightness galaxies may be not dusty or maybe dusty. Actually, until recently, it was assumed that mostly they do not really contain any dust, but 2 years ago, we published a paper where we have shown that a small but not negligible percentage of low surface brightness galaxies actually may contain a significant part of dust, may have a non-insignificant dust attenuation. So this needs to be taken into account as well. You may be aware that with the LSST data alone, estimating the dust content of galaxies is going to be tricky without any infrared data. But this is the paper some of you at least were co-authors. We tried, this was the work led by Kasia Małek, tried to make a kind of estimator of dust attenuation without infrared, based on the optical bands, LSST like. This was done using the SDSS data, And actually, it seems that if we have at our disposal U and R bands and surface brightness measurement in the U band, for some reason other bands do not work that well, we can get a pretty reasonable estimate proxy of the dust attenuation. Non-ideal, but better than nothing. Now we have ongoing work using simulations, trying to see if it can be well reproduced and maybe pushed into low surface brightness regime. And based on simulations, it seems that simulations, high quality dust including simulations seem to allow to see the same kind of relations. So with the LSST, we will try to pursue this route to try to see if maybe we can understand this part better. Then next challenge with the low surface brightness the galaxies is finding them. And as all of us know too well, finding them is one thing, but then making sure that they are actually low surface brightness galaxies and not some kind of artifacts is the real challenge. So this is where probably in the future we will really have to concentrate our efforts on. So here again, last year we have a nice paper based on the dark energy survey data where we adopted transformers for this particular task. Not surprisingly, we found that the most important factor in getting good results is a properly well-prepared training sample. And what's crucial, it's not only the part of the training sample with the low surface brightness galaxies, but what is even more important is the part of the training sample with the false positives, with all possible artifacts. But having that, and in this case, having self-attention based encoder models, they seem to work better than more classical machine learning approaches. Here we could do quite a good job, identify almost 300 low surface brightness galaxies in the DES data, among them 400 new and 276 new ultra diffuse galaxies. So here you have an example of such a galaxies. Yesterday, Krishnan have shown you that they appear in different varieties, for example, blue and red, which are differently clustered. Kai here asked how are the properties of these galaxies in the clusters. So here, indeed, we looked at 7 clusters which are in the field we explored, and we have found that the dependence on properties of these galaxies on the distance to the center of their clusters is well, very scattered, first of all, but there are weak dependencies like towards the center of the clusters. The low surface brightness galaxies tend to be redder and more compact, less spread. Of course, this is all based on angular data. So with 3D data, it may get better, but not with LSST unless we have redshifts. Speaking of redshifts, we have to remember that once we identify galaxies from the photometric data, they are still candidates, formally speaking. So it's nice to have the spectroscopic confirmation. So here we have ongoing observations of a selected subsample of our ultra diffuse galaxies from this sample, and actually it is confirmed that they are what they think they are, and they even have very nice emission lines from which we will be able to tell more about their properties, hopefully very soon. One more ongoing work on this specific sample is based on the fact that in the original work I have shown, the requirements for galaxies to be identified as low surface brightness galaxies were very restrictive. In particular, we requested that they are well fitted with a Cersei profile. So if we loosen these requirements a little bit and we allow them to be fitted with a double Cersei profile, which again, very roughly can be translated to them being nucleated sources with stronger nuclei. It looks like some of the objects in our old sample we can identify as nucleated, and we can double the sample, almost double the sample. This sample is still being tested. This work is ongoing, and it looks like nucleation is a strong factor in as a property of a galaxy. So doing some kind of unsupervised clustering, we can really see that these galaxies may form groups in multidimensional property space. But nucleation is really an important factor. So, as Unikrishnan has shown yesterday, these galaxies display very different dependence on the environment, depending on whether they are red or blue. Then one of the other works we have done recently was actually going two ways. One task we had was to see if the desk experience and desk training sample we obtained so far can be easily translated, transformed to other data. For example, in this case, HSC, but HSC is only one small step from LSST. And this was the work done only on one Abel cluster. Here we had access to dedicated HSC observation of this cluster. And actually what we found was that our transformer models with this identified training sample in this cluster could undergo very successful transfer learning, allowing to discover, to detect new low surface brightness galaxies in these very clusters, among them also ultra diffuse galaxies. So transfer learning with some knowledge how to do it properly, of course, not completely automatically, can work here very well. And here we see again that we can study the dependence on properties of our galaxies, on the distance from the cluster center. And we also see what we have seen in the clustering analysis before, that low surface brightness galaxies like to live in the clusters, but not necessarily in the centers. In the centers, there are much less of them. Ongoing works are also based on HSC data in North ecliptic pole data. Here we have already identified and now tested sample. Same with the kilodegree survey. Here we find such beauties like ringed low surface brightness galaxies, for example. And here there are first tests on now simulated LSB galaxies through Rubin Science Platform, and we hope it will be soon real LSST data. So I hope I was on time in spite of all.
Thank you very much, Agnieszka. Do we have questions in the room? Only Christians, do we have questions? Yes, we do have a question in the room.
Thank you so much. This is really cool. So I was kind of curious, like, I know that it says that you didn't try any fine tuning. Did you experiment with like trying it out to see if like maybe that improves it, or if maybe like it affected it in a different way? I know that Demetrios was working with a CNN and was able to achieve better performance with fine tuning.
Yeah, so you mean the transfer from DES to
Yes.
HSC?
Yeah.
Yes. So actually, when I said that it didn't require fine tuning, it was a bit an overestimation. We did fine tune the training data. We transformed each pixel in the training data to what would it be based on surface brightness in the HSC. And actually this seemed to do the work. This seemed to do the job. More augmentation methods didn't change that much.
Thank you very much. You have to give him the microphone. Every time we have to give microphones to people so that, you know, whatever the person says is heard also from Zoom. Have you heard the question and the answer on Zoom?
No, there are no questions.
Yeah, okay. So could you repeat the question? Sorry, I'm really, really sorry. It's total mess.
My question was if they had tried to do any fine tuning of the classifier after doing the transfer learning from DES to HSC.
Thank you so much.
Also, is this
The one you sent, with the one you put on the web page.
There's one on the web page right now.
Okay, now you should go with this one. I'm sorry, we don't have time.
That's okay.
I'm
That's okay.
really sorry. So next speaker is Kai Aaron. Kai.
Yeah.
Is Kai Aaron, and we speak about exploring the dark side.
It's okay. Okay, so hi, I'm Kai. I'm a third-year grad student at Dartmouth College, and I am working on a search for low surface brightness galaxies in year 6 of the Dark Energy Survey. So let's get into this real quick. But first, I really want to thank Bersham Lupak-Deal and Alex Terlica-Wagner, who've been amazing mentors for me during this process, as well as Annika Peter at OSU, Yudo Du and Bilgo Mbabier, who are undergrads at UChicago, who have been amazing help. So what are LSBGs? I know that we already kind of heard about this, so I'll make it very brief. So these are galaxies that are at least 1 magnitude fainter than the ambient night sky in surface brightness, which for DES is fainter than 24 magnitudes per square arc second. They were first theorized by Mike Disney in 1976, and they are extremely challenging to detect, as we've talked about. They are very faint. And it's a challenge to find them. We'll go ahead. We're going to talk a little bit more about formation channels in the next slide. Oh, maybe not. So there's a couple of different formation channels for LSPGs. You can have environmental processes, such as like these LSPGs being in dense environments, that kind of creates these tidally puffed up quench systems that we see in galaxy clusters. But it's also possible that you can create these really blue diffuse systems based on having a high spin dark matter halo for the galaxy, which kind of creates this very extended faint stellar population and also has a drastic impact on the star formation efficiency of the galaxy itself. So I'm going to talk a little bit about the Dark Energy Survey. This is a 5,000 square degree survey of the Southern Galactic Cap. DES year 6 is about a half magnitude deeper than year 3. So if you're familiar with Dimitrios Tanaglias' work on his search for LSPGs in year 3, you know that like we have some deeper coads, and we're going to be able to take advantage of the wide field to search for LSPGs. And just to kind of like tease like the data volume of DES, we have about 11,000 tiles that cover a half square degree of the night sky within DR2, which is definitely small compared to Rubin, but it's a nice, fun little challenge so that we can try to make sure that we're ready. So for our machine learning algorithm, we opted to use a random forest classifier. So we're working on the features of the galaxies themselves. We placed just a simple surface brightness cut on the DES catalogs. And then we give this classifier features such as colors, magnitudes, sizes, ellipticities, things like that, to train it and get it ready to run on the data. We train it on the year 3 LSPGs, as well as a couple of visually inspected regions of year 6. And then we also add in smudges so that we can make sure that we're sensitive to ultra diffuse galaxies. So this is a lovely little image of 194, and unfortunately my animations don't work in a PDF. So imagine that there was a bunch of points there and they all disappeared as soon as we apply our classifier. Oh. Oh. No, it's just me. I'm just loud. It's okay. Yeah. I can definitely be quieter. Further away. Sounds good. Nope, don't even worry. So after doing all this visual inspection, we go through the very intense process of fitting surface profiles to all the galaxies in our catalog. And we end up with these lovely images of the LSPGs that we have. This is about 40,000 LSPGs within DR2. We show spatial plots of the red LSPGs and blue LSPGs. And I'm going to talk a little bit more about this, but just please keep in mind that this is definitely still preliminary. It's subject to change, but not by much. We just have to finalize some stuff. So I was talking about surface profiles. It's an exhausting process. We had about 50,000 objects after applying all of our visual inspection scores. And even after going through fitting surface profiles to these, there's still a lot of stuff that needs to be tended to a little bit. So there's irregularities in their morphology. This can include spiral arms, knots of star formation, and nucleation is a big problem. So we're only doing single component surface profile fits. So realistically, we want people to have access to these galaxies, but we want to have some sort of flag to indicate that there's something going on here that's causing a problem, some sort of inaccuracy to the surface profile. So Bilgoon here has trained a CNN to look at the residuals of the GalFit profiles and identify poor residuals within our sample so that we can have these things be flagged for people who want to use this catalog. Bilgoon is also planning to specifically work on looking for, because right now there's a lot of nucleated things in here, but we can do better if we are to train specifically on nucleated systems. So Bilgoon is planning right now to do double component, 2-component surface profiles for the nucleated LSPGs in our sample, which is super exciting and cool. And you should definitely keep an eye out for his work because he's awesome. We also have Yudo, who's been helping out with looking at the clustering of our LSPGs. So similar to year 3, we find that the red LSPGs cluster more compared to the blue LSPGs. And we also find that LSPGs have a stronger amplitude in their correlation function than high surface brightness galaxies, both in year 6 of the dark energy survey and also in the 2 mass photometric redshift sample. We also have cross correlation functions for the LSPGs that we correlate with the 2 MPZ catalog because they have both a stronger cross correlation And 2MAS just has better redshifts than we have for DES out of the box. Something that we've also been working on is trying to understand the sensitivity of our algorithm. So hidden behind this lovely plot is simulated LSPGs that we've been injecting into the year 6 coads, running source extractor on, and then testing our algorithm on the features that source extractor gives us for these simulated LSPGs. And what we're able to find is that we are very complete down to about 26.5 magnitudes per square arc second. The important thing is that we have this completeness plot period, because if we ever want to make concrete comparisons from observation to theory, we need to understand how complete our sample is. Otherwise, we really don't know if something's missing because it doesn't exist or if it's missing because we just haven't found it yet. But stay tuned. There's more to come on my work with this paper. I plan to have it wrapped up in a couple of months. But I want to talk a little bit about the future of LSPG science with Rubin. So it's been shown that deep learning models, such as convolutional neural networks, can provide more robust detections of LSPGs. Right here, we have the receiver operating curve for our different algorithms to detect these galaxies. And we can see that a CNN has a much higher performance compared to the support vector machine that was used by Dimitrios in year 3 and the random forest that we used in year 6. It's also obvious to me that the current method of refining our classifier output with visual inspection is just not going to hold under the scale of LSST. I cannot look at 50,000 LSPGs again. So I think that the future of LSPG identification is going to lie in utilizing deep learning algorithms and visual inspection. Don't forget that last part. So I am currently working on, I was just awarded the GRFP to train and characterize the performance of a deep learning algorithm to identify LSPGs and LSST. Right here, if they weren't all stacked on top of each other, you can see that we already have LSPGs from our catalog in DP1. We've been working on trying to pull these catalogs and get ready to test the deep shadows algorithm that Dimitrios worked on during his time. We're going to utilize existing precursor data such as HSC, the release of DP1, and the upcoming release of DP2 to help us have a very well-tested, robust algorithm in time for DR1 of LSST. But I mentioned visual inspection, and that's kind of the really cool thing. So I got my start in astronomy research doing citizen science. I am a Galaxy Zoo veteran, and I really would like to bring LSB science to the general public. So our plan is to take the galaxies that are probably the most unique, that don't really fit the typical morphology of usual LSPGs, and have the public do classification of them, assign labels, and we can use that to not only refine our classifier, but also engage with the public so that they understand what's going on. We could talk about the importance of LSPGs and the role of dark matter science. And I think that it would be really great to go forth and inspire the next generation of astronomers. But I'm gonna leave my summary slide. Thank you so much.
Thank you, Kai. And do we have questions in the room?
Yeah, I've got one.
Yeah, what's up?
Do you see any difference in the Sirsic index between the red and blue populations?
That is a very good question. I think that in order to tease out that information a little bit more, we would need to look at our refined sample, which is kind of what we're trying to get right now. But generally, LSPGs have a very flat Sirsic profile. So the highest that you typically see is around 3. But I would assume that they would follow typical galaxy morphology, where our red elliptical dispersion supported systems are probably going to have a higher surface index than our disky systems.
Thank you. Christian, do we have questions online?
No, there is nothing online.
Just a second. Yeah. Okay,
Great
so we
job.
have two questions here.
Great job, Kai. For the residuals, it looked like a lot of them might be nucleated centers. Did you see if there's any spatial distribution to the ones with poor residual fits?
Ooh, that is something we have not done yet, but that is a really good idea. That would be really cool to look at.
Thank you. We have a last question, Jan.
Is there a question back there? Yield my time.
Sorry, Jan,
Okay.
could you ask your
Um,
question?
Hi, Kai. I had a question about the injection and the testing.
Yeah.
Were you injecting sursages? How were you deciding how to inject?
Yeah, so we actually have been injecting with a very broad range of surface indices. So we literally are going from like 0.5 to 5. So they do have a broad range of surface indices, although we don't really expect to find LSVGs with surface indices higher than 3. But the cool thing is that I only showed the surface brightness and size plot there, but you theoretically could make that plot for literally any combination of features. I just chose those because it's the easiest to really like understand physically.
Thank you. Other questions? So we will go to next. Do you have to ask a question? No. Okay, so we go to next talk. Thank you very much again. Oh, sorry, Burcin. Yes. I opened the wrong one. I had to open this one. Yeah, there we go. Go ahead.
I should be also away from the mic.
Yes, please. Just keep.
Okay, thank you.
Don't go too
Oh,
far.
I might
because-
fall. I am
yeah,
super
yeah.
clumsy. Okay, let's see. We will try. Hi all. So I will talk about dwarf galaxies in LSST era. This is different than what I submitted, but I decided that's much more fitting. So dwarf galaxies in LSST era. So before I start, first I will say, why should you care? Why should we care? Because dwarf galaxies are the most numerous galaxies in the universe. They are the building blocks of larger galaxies, so they are crucial for galaxy formation, right? They are the oldest and most metal-poor stellar systems in the universe, so they are probes for the early universe. And they are the most dark matter-dominated systems, galaxies, so they are amazing for understanding of galaxy dark matter, right? So we all agreed we should study and find and study these faint galaxies, right? But traditionally, finding dwarf galaxies was using resolved stars. So initially, you get the image, create the catalog. If you plot this spatially, you will not see anything. But if you select the stars in color magnitude space, well, you will see an overdensity, smooth it, voila, you discovered an ultra-faint dwarf galaxy. Congratulations. With that, this technique has been quite successful for 2 decades. We have discovered ultra-faint dwarf galaxies, many ultra-faint dwarf galaxies in local group, and even faint dwarf galaxies out to 5 megaparsecs. So it has been quite successful. And we did a little experiment and tested how well we will be able to find these dwarf galaxies in LSST era. What happened is we had a very deep Magellan image comparable to 10-year depth of LSST. And we created observations of various dwarf galaxies, different size, shape, and luminosity. And we injected those in 3 fiducial distances. This is the results for 1.5 megaparsec, which is like edge of the local group, right? And I am showing the results in size and luminosity plot. The dark blue means high detectability, yellow means low detectability, and the image that I am showing is mock observation that we created. So basically, we will be and the data points are from the known dwarf galaxies that we know. Okay, so in LSST era, in 10-year depth, we will not be only sensitive to the dwarf galaxies down to absolute magnitude of -5, we will be complete to the dwarf galaxies at edge of the local group. So this is fascinating. And what about 3.5 megaparsecs? So we are going a little bit further, and now our sensitivity plot change a little bit, but we are going to be complete for the census of the dwarf galaxies down to absolute magnitude of -7, which is the bright ultra-faint dwarf galaxies. And then at 5 megaparsec, the completeness drops a little bit further, but we are going to create the complete census of dwarf galaxies at 5 megaparsecs down to absolute magnitude -8, which is the faintest classical dwarf galaxies. So this means we are not only going to find ultra faints in local group, we are going to have a complete sample in local volume in LSST era, which is great. But after 5 megaparsec, we get a diminishing results. So how can we solve this? There's a complementary technique, which is integrated light searches. Laura will talk about more, so I will leave it to her. But basically, you have the image, you remove the bright objects, smooth it a little bit, and the diffuse things pop up. And this technique has been quite successful between 5 megaparsecs to 12 megaparsecs, and discovered many faint dwarf galaxies in local volume. But these two techniques failed to find this little guy. This is Tucana B, and as you can see, it has a bunch of, it is not completely resolved. It has a few resolved stars with some unresolved light, and it has been discovered with visual inspection. And when we discovered this, we get the deep imaging and resolve the individual stars, and it is at the distance of 1.4 megaparsecs, and you can see there is no young stellar population in it. And based on distance that we got, nearest galaxy is 500 kiloparsec away. So it is an isolated quant system. And when we put it into a size-velocity plot with the other known quant isolated systems, you can see it here, right? It is the smallest and the faintest one. And given its isolation and physical properties, it might be a definitive example of an ultra-faint dwarf galaxy that has been quenched by ionization, which is quite important confirmation for the key driver for the galaxy formation on smaller scales, right? This is quite cool, but we only discovered this galaxy because one day Dave Sant was looking at the legacy viewer and find this interesting guy, right? But in LSST era, it is not feasible for Dave Sant to look at the LSST full, or he can do it maybe, but we said that it is we probably need a solution. So this motivated us to start this seamless project, a semi-automated machine learning search for semi-resolved system. So we have well-resolved regime, unresolved regime, and there is this sweet spot where we can actually find the faint, distant dwarf galaxies. So here is our team, and even our logo is moving from resolved to unresolved. So it's quite cool, I think. Anyway, the technique that we are using is, again, traditional low surface brightness search, integrated light search from smudges pipeline, which delivers about 1 million candidates. Then we have a CNN algorithm, which we train with the known resolved and semi-resolved objects, which gave us 1,000 candidates. And then we had a mini universe project for ourselves, which we identify high confidence candidates, which include both star forming and quant systems. And now I will focus on 3 of those, which are Pavo, Corvus A, and Camino. And I will also mention that Camino was independently discovered with Kai's LSPG search, which is great. We discovered these galaxies, as you can see, they are partially resolved. So resolved search would fail on those. And then we get HST data, resolved completely. If we resolve them, we should look at the color magnitude diagrams. Here are color magnitude diagrams for each. So old stellar population and young stellar populations are visible there. And POVO is at the distance of 2 megaparsec, with some young stellar populations as young as 150 million years old. And then in Corvus A, it is 3.3 megaparsec, has young stars as young as 50 million years old. And Camino is a little bit further away, 6 megaparsec away, and it has stars as young as 30 million years old. So now that we have the distance, right, let's look at the environment. And we also highlighted other non-local volume galaxies in low dense environments. Okay, so here is our first one, POVO. As you can see, it is quite isolated from other known systems. And here is Corvus A, again, far away from major systems. And here's Camino, is even more isolated. So the nearest galaxy to each system is about 1 megaparsec away. So this is, I am emphasizing this is one of, so they are among the most isolated systems. I am emphasizing this because so far our understanding of dwarf galaxies mostly rely on satellite galaxies. Although isolated galaxies are quite pristine environments because they are free from the effects from a major galaxy. So this is quite exciting. And we look at the size luminosity plot, and again, we plotted other colored marks are isolated dwarf galaxies. As you can see, our targets are consistent with the known systems, but also isolated galaxies seems to follow a trend in more compact regime, which can be just an observational bias, but we are in the process of working on our completeness for our project. So hopefully we will have more idea what's the true distribution. And so, but our goal is basically with seamless. When we look at this plot, we have a stellar mass and distance. The blue ones are the shield sample, which are the isolated galaxies that are identified with H1 survey, right? Closer we have Tucana B, our isolated ultra-faint, and Sculptor A, another ultra-faint dwarf galaxy that was also identified with Dave when he was looking at the legacy viewer. So, and we have the Leo P. That's it. We don't have anything else. So, but with C, and our goal in Seamless to like fill up this gap between the nearest things and the more distant star-forming region. And our three objects are nicely already showing us how successful we are in that regime. So one other thing that I will emphasize is we derived these star formation histories for our galaxies. For first, I want you to focus on this slide. So this is a study done by Christy McQueen using JWST and deep HST data. So they focused on near isolated dwarf galaxies and derived these nice star formation histories. And they, as you can see, there is a common pause after ionization in star formation, and they suggested maybe this is a common feature for isolated dwarf galaxies. So then we recreated this with our sample, right? And we edit our sample to that plot. And as you can see, although maybe POVO and Camino might be consistent with it, like because we have uncertainties, right? But Corvus A doesn't follow that trend. So maybe that suggests a diversity in star formation histories for isolated dwarf galaxies. Although I should just say our data is much shallower, so deeper images are needed. But this is also what simulations are predicting for isolated dwarf galaxies. So with more systems, hopefully we will be able to answer this quite much better. And with the Seamless project is a precursor LSST data, and it will also provide a very nice training set for LSST in near future. So my takeaway points: dwarf galaxies are cool. Semi-resolved dwarf, semi-resolved regime is haven't been explored yet, but we must explore it. Seamless probes this regime successfully, and Pavo, Corvus A, and Comino are among the most isolated faint dwarf galaxies. And with Rubin, we will even reach more distant faint dwarf galaxies with similar CNN algorithms. That's it. I'm done.
Thank you very much, Burçin. Do we have questions? Yes.
I actually have a general question. I'm trying to figure out how we're going to do seamless with LSST, whether we do, how we do this. So do we have to go to the Rubin Science platform, apply our algorithm that finds low surface brightness objects, and then somehow run our CNN on the Rubin Science platform? How does this, how are we allowed to do this science project? But do you know that, or are you be allowed to do that sort of thing on the Rubin Science platform?
I don't know the answer actually. Do we have
I mean,
somebody?
this clearly something people will want to do, right?
Yeah. Yeah.
I think the partial answer that, or partial answer that I would give is one, I think workflows like that, probably for the training of your machine learning model, the best path forward would probably be to, create postage stamp images, which you can download and use to train your classifier, and then run the classifier in the science platform is one path. And then the other thing I was going to mention is that eventually, right now it's kind of not needed, but also we just haven't stood it up yet. Eventually there will be batch computing resources available to users, and I forget what it's called, but a committee that will allocate time, kind of like a TAC, basically, for batch computing.
So can we go to
Something
the
like that, yeah.
next question for Burçin?
So I think it's really neat that you're seeing these things and they're turning out to be like little blue fuzzy things, right? Like quite notably so. I wonder if you've thought more about how that connects to the fact that they're isolated and therefore near voids, right? Because there's this whole story people tell about voids being essentially the clock runs slow, right? The universe is younger in a void is sort of one way of thinking about it. Does that fit with the three objects you were talking about, or are they either too far in the void or not far enough in the void for that to really be the story? Fair. We should talk about it later. That's fine. Yeah.
Thank you. Let's thank Burçin again. And next talk is Laura Hunter.
So I'm going to continue the trend of Dartmouth people being very loud and step away from the mic. Can you all hear me? Awesome. So I am presenting ID Mage, which is a search for dwarf galaxies around MC analog galaxies. Working with a number of people in this room, Burçin, David Sand, and indirectly with Kai and Jeff Carlin and others. So this is great. So Burçin and Kai gave a great introduction of why we care about faint small galaxies. So I'm just going to focus on why do we care about satellite galaxies specifically. it's a trace of dark matter halos is the long and short. You have your central dark matter halo, you have your central galaxy, and you have your sub-halos in which satellite galaxies form. And we can't go out and count dark matter sub-halos yet, but we can go out and visually count satellite galaxies in order to try and get an idea of how many subhalos there are and what is the population function and the mass function of those subhalos based off the luminosity function of the satellites. Currently, the best known system we have for satellites is the Milky Way itself, where we know dozens and dozens of satellites to very, very faint magnitudes all the way up to the LMC. And there's more added semi-regularly when big surveys come out. Because we know the Milky Way and the Andromeda systems, we've gone out and looked for satellites around other similarly mass systems with surveys such as ELVS and Saga and so on, finding well over, searching well over 100 hosts for their satellite systems and building up this massive statistical sample that we can use to understand our models of dark matter and the universe. The one problem is we now have a really nice pin for things around this massive Milky Way, but we don't have a comparative sample for lower mass galaxies. And when you don't have that, you end up with a large range of predictions for how many satellites these lower mass hosts should have. And so other surveys such as MadCache, Delve Deep, ELVS Dwarf have begun looking for satellites around similarly massed hosts using a variety of techniques. IDMA just happens to be the one that's doing the most hosts all at the one time in order to build up this large statistical sample to say which of these models is most correct from what we see. So now we're going into how are we finding these things, and Bershin set me up beautifully for this. So this is a search for low mass galaxies around small galaxies. This is a systematic search using the legacy survey data. So this is all publicly accessed data that we downloaded the footprint of our hosts around out to the virial radius, and then a little bit more in order to account for uncertainties in distances and mass. And this is all to test cosmological predictions. So here we show the host selection. I mentioned ELVS and Saga as the big Milky Way searches. You can see the ELVS hosts, which are at a similar distance to our hosts that are, again, Milky Way mass. And then my IDMage are the red, which are similar in size to the LMC and SMC based off K-band luminosity. And then you can see Delve Deep and MadCache over in the yellow, which are similarly masked but different search techniques. And then ELVS Dwarf, which is similar galaxies and similar range, but in different environments. These are all galaxies that are 10 to the 10 to 10 to the 8 in stellar mass, again, based off K-band luminosity, with 36 hosts in total, making up 35 host systems, as one seems to be a binary pair of galaxies. Of these, 17 are going to be in LSST, which means we get to go deeper soon. And they are in a wide range of environments. They range from within small groups of other low mass galaxies, as you can see here. These are all the objects within 500 kpc projected and 1 megaparsec in distance. And so you can see the NGC 4244 has a bunch of smaller galaxies nearby it. The ESO 364 G29 has 2 that are within 1 megaparsec, and then UGC 4115 is off on its lonesome. And the black circle corresponds to the projected virial radius, and the gray circle is how far we searched out in these galaxies. So for LMC mass galaxy, our search radius matches well with the virial radius. For SMC, we're going out a bit farther. But again, this does cover for the uncertainties in distance and mass. As Berchin brought up, this is an integrated light search, which means we're going through and we're looking for tiny smudges. We're not counting stars. these are all unresolved. And to do this, we're using a program written by Paul Bennett, which was published in 2017, which goes out, masks all the bright stuff based off like guide star catalogs and known galaxies and stars, masks everything out, makes the circles big enough to get the halos and everything, and then spatially bins all the images in order to make the faint objects pop up more. And then we use source extractor to find all of these faint objects. This does leave us with a bit of a high false detection rate, where we get a lot of things like the en masse outskirts of bright galaxies, diffraction spikes, cirrus, so on and so forth. So a fast initial visual inspection is done to clean out the clear trash and get rid of all of the things that are just automatic. That's cirrus, that's cirrus, that's cirrus, that's a diffraction spike. And then the higher quality targets are put up into a private Zooniverse in which experts at satellite galaxies and low surface brightness galaxies did visual inspection and rated the candidates for continuation in the sample. And we found that we had a bit of a completeness issue when we compared what we found at the end by visual inspection to what we predicted based off the algorithm completeness, which is shown up top. And then when we looked at what we found, we noticed there was a disconnect with the low surface brightness stuff. And so we went through, redid the Zooniverse, but this time added objects from smudges and elves, which were similar distances, similar surface brightnesses, as well as fake objects that were generated with similar surface brightnesses, colors, and surface indexes to the expected, to see how the visual inspection was impacting our completeness and our recovery. And we noticed we lost about half a magnitude in surface brightness completeness when we accounted for the visual inspection component of the search, which is shown below, where you can see basically one is how people rated everything of that end up in the sample. And then on the left is how everyone rated the highest likelihood objects. And you can clearly see the impact of the visual inspection on all of this. Overall, we're roughly complete down to an absolute V-band magnitude of -9 and a surface brightness of 26. We found 355 objects of interest, 264 of which are new, and 134 of which make up the high likelihood sample, of which ones were highly rated by the Zooniverse and have follow-up. Have follow-up, not and have follow-up. So now that we have all these objects, we can start to say, does this agree with what we expect to find? And we find, yes, these are similar in size, surface brightness, and magnitude to the ELVES sample, which again is a selection of low mass galaxies at the right distance found through integrated light techniques, so it's quite comparable. You can see in the different colors, the yellow are ones that were known and have distances or velocities in agreement with their hosts. You can see those are pretty bright high surface objects. The pink are the ones that were very highly rated that don't have follow-up yet at the beginning of the survey. You can see they fall really well in the space where we expect to find these galaxies. And then the blue are the objects of interest, which tend to be fainter, more compact, and have properties that make them less likely to be satellites, but still we're interested in them. Using the most, like the sample that was rated most high likely, we can put an upper limit on how many satellites we think we found, which is about 4 satellites per system for the LMC mass systems and 2 for the SMC mass hosts. We also used the radial distribution of the satellites to make an estimate of the lower, to correct for the background, which we expect is fairly even across the spatially even And if we account for the spatial distribution, we think it's about 1.6 per an LMC and 1.2 for an SMC. But again, we need to do a lot of follow-up to know. If we use our upper estimate, this is what we find in comparison to simulations, and it is well above what we expect. But again, follow up, follow up, follow up. And as anyone who's ever tried to study faint galaxies will say, distance, it matters, is also one of the hardest things to measure. And so we have roughly 355 objects of interest to go out, and only about 20 of them already had distances or velocities. And right now we are using every telescope we can get our hands on to try and get either velocities, because if these objects are associated with their hosts, they should have similar relative velocities within a few hundred kilometers per second. If they have more than a few hundred kilometers per second, we can confidently say they're not associated. The other option for distances is surface brightness fluctuations from the ground, where we can get a pretty good constraint on the distance and say, hey, these are very likely associated. And we're also using these to get other properties of our galaxies, such as H1 mass and velocity at the same time using GBT. And so that's what I'm working on right now. We have something like 70 that we have velocities for, and then 20 to 30 that we have, I think it's 20 something, that we have the photometry to do the SPFs on that are in the pipeline. So that'll get us a really nice sample that we can clean out and update our luminosity functions. With the last few minutes, I want to mention this is all done with public data, which means when LSST comes out, we can just download and go again. And this will improve depth on our hosts that we've already searched, greatly improve the number of hosts we can go, and we can really start pushing down and building up this sample more and more and more. And we can go out a little farther, especially as the years go on and the data get deeper. And we're super looking forward to that. But we do have some limits here once we hit because of LSST and huge coverage. There's a lot of visual inspection in this, which requires a lot of people hours. Hopefully some things like Seamless and Kai's search algorithms will help us classifiers will help us remove a lot of the human hours, speed up the process, improve that. The other thing is, there's been all this talk of these template images, which are done with the better seeing, the best seeing, and can we access those and use those for surface brightness fluctuations for these, and really cut down the amount of unique follow-up data that we need, and use this discovery data for the follow-up data, such as is used in LSTORs when they do the HSC imaging for both the detection and follow-up. So thank you all for your time, and coming soon is Hunter et al. In Prep, which is the first release of our updated our velocities and distances. We'll have updated luminosity function, and there's a lot more to come in this era. Thank you.
Thank you very much, Laura. Do we have questions in the room? I asked first if there are questions online because they didn't have any space. Do you have any questions online? Uni, Krishna?
No, I don't see
No.
any
Okay,
questions
so
online.
Brian.
Okay. You find any star cluster populations in these?
We haven't been looking yet. We've mostly been focusing on identifying potentials, and now we're getting to search individual. Once we have the sample cleaned, we'll start looking at the individual properties, such as what's their star formation rate? Are things quenched? Are they gas rich? That is why we need the clean sample.
Thank you. Kai? Wait for the microphone, please. Please, please, please.
This is a great talk. I was kind of curious if you have thought about trying to do like surface brightness fluctuations or anything else to try to get distances. It's entirely possible that that might not work. I just realized I'd never asked.
We have the photometry from like Gemini North, some coming in from Gemini South, as well as like MegaCam and an upcoming run on IMAX to get photometry for surface brightness fluctuation. We are currently talking with an expert in SPF in order to help us process that data. So we have the data in hand and are really looking forward to those results.
Thank you. Other questions? Okay, great. Thank you again, Laura. No, I'm sure, yes. And our next talk is in remote. Alexander, are you connected?
Yes.
Please go ahead and share your talk.
Can you see my screen now?
No.
We can see it online.
Can you see it now? No?
Okay, now we see it. Yes.
Okay.
Perfect.
Okay. All right. Hello, everyone. So I'm going to talk about the periphery of edge on galaxies seen in deep imaging. And so I'd like to start with the motivation behind this work. And so the outer regions of galaxies, the outskirts, hold crucial information about how galaxies form and evolve over time. And so these regions, they include different types of structures, stellar halos, tidal features, and other distinctive features which are only visible in deep imaging. And so by studying the periphery of galaxies, we can trace the formation history of galaxies, whether they have experienced recent mergers or accretion events. And we also gain insight into how their disks have grown over time, and also about the shape of dark matter halos and the dynamics of dark matter halos in these galaxies. And so there are different types of tidal features, like stellar halos. These are essentially tracers of accretion and satellite disruption, and also tidal tails, streams, tidal spirals, ripples, plumes, and other types of features which are evidence of ongoing and past mergers, and also thick disks and flares, which essentially demonstrate internal dynamical evolution in galaxies, but they can be related to interactions and satellite accretion, and low surface brightness disks, which originate from gradual gas accretion and low star formation efficiency, and some environmental effects, and of course disk warps, which can also have different origins. They may result from interactions and misaligned accretion and even dark matter halo torques. And so in this study, we explore edge-on galaxies because they reveal the vertical structure of the vertical and radial structure of the disks, and also other structural components like bulges and bars. And we can easily detect flares and warps in these galaxies, and other types of features, including LSB features, specifically polar structures. And all of these factors can actually can help us better understand how galaxies form and evolve, and can help us constrain our models of galaxy formation and evolution. This is one of the goals of the study, to compare observations with simulations. And so we recently published 2 papers on these 2 intriguing galaxies, UGC 4599. It's a spiral galaxy, and the interesting fact about this galaxy is that the spiral structure is only seen in deep imaging. And on the right, you can see 2 deep images from the Huron telescope and LDT telescope. And you can see that the spiral structure is extremely faint, and it's embedded into an extremely faint stellar disk. And the spiral structure is also seen in the H1 map. And so basically all of these observations are consistent. And so this is a giant low surface brightness galaxy with a diameter of up to 100 kiloparsecs. And the other galaxy is UGC 1043. And here you can see 2 deep images of this galaxy from the Desert Legacy Imaging Survey, and taken by the ARC 3.5 meter telescope at Apache Point Observatory. And both images reveal a very thick envelope around a super thin stellar disk. And this galaxy is actually a polar bulge galaxy. It has a very unusual bulge, and it has several satellites, satellite B and satellite and Galaxy C, and they probably interact with the galaxy. We can see this through the bridges in the optical and also H1 map in the bottom. And so both of these galaxies demonstrate the importance of using deep photometry to better understand how galaxies form and evolve. In our recent study, we also selected a huge sample of edging galaxies, specifically 800 edging galaxies from the SDSS Stripe 82 survey. And we actually used 3 different sources of data: SDSS Stripe 82, HECSSP, the deepest source of imaging, and also DESI legacy imaging surveys. And by comparing these images, we can actually more reliably confirm whether we see a tidal feature or maybe it's just an image artifact. And so we see that only 50 galaxies in this sample demonstrate tidal features with the average surface brightness down to 27 magnitude per square second in the R band, which is only 6% of the entire sample. Also, we have been working on the largest atlas of low surface brightness features in edging galaxies, which is based on the Aegis catalog of edging galaxies, so about 6,000 of galaxies. And here we also use different sources of imaging, and we enhance these images by stacking several filters together to increase the signal to noise ratio. And so we have classified all these tidal features into loops, shells, bridges, and other types. And you can see that the total percentage of all these features is just 3%, which is lower than in the Stripe 82 catalog. And this is probably related to the fact that the Aegis catalog is dominated by late type spirals, which do not typically show a significant number of low surface brightness features around them. Also, we checked our results if they are contaminated by galactic cirrus, which is scattered light, scattered of dust particles in our galaxy. And in deep images, galactic cirrus can be quite annoying because you can easily confuse extragalactic features with galactic cirrus. And indeed, 11 galaxies in our selected sample of galaxies with low surface brightness features demonstrate significant cirrus contamination. But in fact, none of them wasn't excluded from consideration because either these galactic filaments, galactic cirrus filaments are easily distinguishable, or they have different colors or different morphology, geometry, and so we can be quite confident that the features we observe are not confused with galactic cirrus. And also, one of the goals of this study is to compare observations with simulations. So first, our results are in good agreement with the literature. We see that from 3 to 6% of galaxies, they demonstrate low surface brightness features with a surface brightness limit of 28.5. And of course, the surface brightness limit is very important here, because if you go deeper, then you can probably see more and more. And also, here I present this figure from a paper by Mira Cratera et al. 2024, where they studied how cosmological simulations compare with observations. And so they used different types of simulations, specifically the TNG50 simulation, and they degraded their images, added some noise and PSF and other things to better match observations. And so we see that basically observations compare pretty well with simulations, at least with the Auriga and TNG50 simulation. Of course, it depends on the framework of that specific simulation, the physics they incorporate in their simulation. But the general agreement is pretty good. And of course, there can be some other biases, not just selection bias, but redshift bias. And of course, it's easier to identify low surface brightness features in local galaxies than in more distant galaxies. And here on the right plot, you can see that we can see more structures, tidal structures in a local universe, in local galaxies than in more distant galaxies at higher redshifts. And another type of bias is due to mass, and this is a physical bias. Of course, that's how galaxies form through hierarchical buildup. We expect to see more tidal features around more massive galaxies, and this effect is well illustrated here in both plots. We can see that galaxies with tidal structures are found among more massive galaxies. And also we measured some characteristics of these tidal features. And here in these plots, you can see that essentially we don't detect any features with average surface brightnesses fainter than 27 magnitude per square second, which is probably limited by the surface brightness limit of these surveys we considered in our study. And the final part of my presentation is this clearing, warping, and lopsidedness, which can also be studied in using edge-on galaxies. So here we compare simulations and observations. We use the TNG50 Skirt Galaxy Atlas, which consists of 1,100 galaxies. So here we can see some examples of these galaxies, and in our study, we use their edge-on orientations. And so to measure disk warps, we use a pretty straightforward method. So we take two isophotes at 24 and 26 magnitude per square second, which are depicted here on the left by two contours, red and blue contours. And then we can find the average lines of these contours and measure the warp angle, the amplitude, and also the lopsidedness of this galaxy by just comparing the left and the right sides of the galaxy. And then to measure the flaring effect, we can do photometric cuts perpendicular to the galaxy plane, galaxy major axis, and just fit these profiles with some function, for example, exponential or isothermal disk function, and determine the disk scale height for these cuts, and then just determine how the disk scale height changes with radius, and essentially measure this flaring effect. So this has been done for both Aegis and TNG50 galaxies. And here you can see the results. That's how we define the lopsidedness of the galaxies, just by comparing the radii of the left and the right sides. And for both isophotes, we can see pretty good agreement between the simulation and observations. And this is for the warp angle. And here we see that for the 24th isophotes, the TNG50 has a broader distribution for the warp angle. But at the 26th isophote, these distributions become more consistent. And also, this is
30 seconds.
These are the histograms for the warp
The
type.
conclusions.
And essentially, we conclude that except for disk flaring, galaxy simulations are comparable with observations. And yeah, so we see that warping, of course, increases in deep images, but lopsidedness remains nearly constant. Thank you for your attention.
Thank you so much. Do we have questions for Alexander? Not in the room. Do we have questions online, Uni Krishnan?
No, we do
Or on
not.
Slack or Zoom?
No.
No. Okay, so let's thank Alexander, and let's thank all the speakers for these wonderful talks. We had the wonderful overview on low sulfur brightness features and galaxies. Thank you very much. Have a nice evening. Bye-bye.